So to this point, we've done integration by approximating using rectangles, and by having functions that we know the antiderivative for. So like e to the x, we know that the function whose derivative is e to the x is e to the x. And so relatively straightforward integration or antiderivatives. You'll hear those words used interchangeably. They mean the same thing. What we're going to start today is the method that we can use to integrate or find the antiderivative of a function that results from the chain rule. And then next week, we'll look at the product rule. So we have find the integral of 2x times the square root of 1 plus x squared dx. So to this point, we really don't know what to do. We sit and wait for Mr. Gingrich to tell us the answer. What we're going to do is we're going to introduce something new. We're going to let u equal the thing that's inside of the square root, or that's being taken to the 1/2 power. And then we're going to take the derivative of u, or the differential. Du would be equal to 2x dx. And what we're going to do is then make a substitution into our original integral. So the u will be taken to the 1/2 power. The 2x dx will be replaced by du. So we can show that substitution, and then the u to the 1/2 du, I can integrate because I already know how to deal with a variable to a power. So I add 1 to the exponent, so I get u to the 3/2, multiply by the reciprocal of that power, so that's where the 2/3 comes from. And then because I don't have any limits on my integral, I have to add a constant. So we just call it c. Unfortunately, my integral is in terms of u. My original function was written in terms of x. So I will back substitute and replace the u with what we said u was equal to, which was 1 plus x squared. And we get our final answer. So here is the general substitution rule. If we have u equals some function g of x, and that is a differentiable function whose range is an interval I, and if f is continuous on I. So we need that so that the composition of f with g exists. And then if we have f of g of x times g prime of x dx, we can rewrite that as f of u du. Excuse me. So instead of having this product, we end up with a single function in terms of a new variable now, u instead of x. So substitution rule, more often than not, we're going to have a composite function. I mean, that's what we're told here. We have a composite function. So things like square roots of functions or any root of a function would be an example. A trig function where we have a function inside, like sine of 5x, that technically would be a substitution rule problem. E to a power, where the exponent is a function, that would be another time when substitution rule is used. Also with fractions, 99 times out of 100, if we're taking the integral of a fraction, the denominator is going to be our u. And I think the one time out of 1,000 is one of the examples you'll have in your homework. So that's something to look forward to. All right. So here we have 2x plus 1 to the 1/2 power, or the square root of 2x plus 1 dx. If you trust in what I just said, I'm going to rewrite this quick. If you trust in what I just said, our u would be the inside of our function. And then we would need to find du. What is the derivative or the differential of 2x plus 1? What do I get when I take the derivative?
Two.
2, exactly. And actually, because it's a differential, we're going to get 2 dx. Now, when you look at our original expression, I can see where the 2x plus 1 is. I don't have this constant of 2. So oftentimes that happens where we're missing a constant. So what I'm going to do is, where I have du equals 2 dx, I'm going to divide by 2. So what happens when I make my substitution, I get u to the 1/2, and the dx gets replaced by a 1/2 du. And the 1/2, because it's a constant, I can write that out in front of the integral symbol. You could leave it inside as well, it doesn't matter. I like to separate it. Now we take our integral. So we get 1/2, because that's what's out in front. We get u to the 3/2 power, and we need to multiply by the reciprocal of that power. So we get a 2/3. Because there are no limits on our integration, we have to add a constant. For these, I would simplify. For instance, the factor of 2 cancels. And the last thing I would do is rewrite it in terms of x. So 1/3 times 2x plus 1 to the 3/2 plus a constant. All right, so for this one, calculate the integral of tangent of x dx. And looking at it, I don't see where I have a function and its derivative in this problem. However, I see a wonderful trig function. So I am going to rewrite my trig function. Tangent is the same as sine x over cosine x. I am going to let my u be equal to my denominator. And if you're ever in doubt for what you should have as u, pick something from the function and take the derivative. And in this case, I have a sine x and a dx. I don't have that negative. So just like we did with the previous problem, I'll divide both sides by -1. Or if you don't like division, multiply both sides by -1. So I have my integral. The sine x dx gets replaced with a negative du. And the cosine, which is in the denominator, gets replaced with u. So one question that often comes up on this problem is, why don't I let u equal sine of x? And the reason is, when I take the derivative, I would get cosine, but the cosine in the derivative would be in the numerator, and I needed cosine in the denominator. So I need to use that. I need to use the denominator as my u. All right, integrate. I know I'm going to get a negative. What function, when I take its derivative, gives me 1 over u, or 1 over x? ln. Now, one thing we have to be careful of, in this problem, u could be positive or negative, but ln is only defined for positive values. So we are going to include, anytime we take an integral and get ln, we're going to include absolute values. And then we're going to add our constant because it's an indefinite integral. Substituting back in, u was cosine of x. And you often won't see it written this way. The reason is I can write it without that negative in front. This would be the same as the ln of cosine of x to the negative first power, not the inverse cosine, but cosine to the negative first, or 1 over cosine. And 1 over cosine is secant. So this is the way you'll most often see it written. This is equally correct. Again, on the AP exam, on the multiple choice section, you might see it written the second way rather than the first way. On the free response section, either way would be accepted and correct. All right, so this is the first part of your assignment. Page 381, 1 through 6. All, and then 7 through 19, just do the odds. In 1 through 6, the book actually helps you out a lot by telling you what the value or what you should use for your u. And then 7 through 19, you're on your own. The second part of your assignment is going to be actually doing definite integrals. So plugging values in and simplifying. So we'll do some examples of those as well. Let's see. New share. So if we continue with the substitution rule, and I will have these as 2 separate assignments in Schoology, so you get double the points. Yes. So for definite integrals, the substitution rule says if our derivative of g is continuous on the closed interval from a to b, and our function f is continuous on the range of u equals g of x. In other words, again, our composite function is defined from a to b, then we can substitute and get f of u du, and we can also make a substitution for our limits. You don't have to. Some people don't like doing it that way. I think it saves a step. And I'll show you here in just a minute what I'm talking about. All right, moving on. So we did this indefinite integral, 2x plus 1 to the 1/2. Now we're going to do it with a definite integral. We're going to evaluate from 0 to 4. Let's try this again. And so our substitution before, we let u equal 2x plus 1. And then our du is 2 dx. And so we divide because we didn't have the 2. We got that 1/2 du equals dx. The thing that I like to do is now replace my limits as well, or substitute my limits as well. So my lower limit is going to be, or my new lower limit is going to be the value I get when I take this lower limit 0 and plug it into whatever u is equal to. So I get that my new lower limit, if I leave everything in terms of u, would be 1. And my new upper limit would be the value I get when I plug my old upper limit in for x in my equation u equals. And I think that's a 9. So now I can rewrite everything. I'm going to put the 1/2 out front, take the integral from 1 to 9 of u to the 1/2 du. And where this helps is in the final evaluation. Because I changed my limits, I don't have to substitute the 2x plus 1 back in. So it's really your choice. If you want, you could plug the 2x plus 1 back in, and then you would use the limits 0 to 4. Or you could change your limits and use the new limits and just use u. And I'll show you with this example how it would look if you didn't change your limits. Um, 9 to the 3/2 would be the square root of 9 cubed. Pretty sure that's 27. I'd ask you guys, but none of you ever respond. So, oh, sorry, Grace, you have in the past. So we'd get 26 over 3. If you didn't change the limits, and what I would do then is I would say I still have the 1/2. It would be my integral from x equals 0 to x equals 4 of u to the 1/2 du. This just reminds me that I can't just plug in to my u with those values, because those are values in terms of x. And so I would get my antiderivative, and then I would, again, you could simplify if you wanted at that point. But then we would need to plug in 2x plus 1 to the 3/2. And now I can evaluate from 0 to 4. And what happens is I plug 4 in, my upper value for x, and I get 9 to the 3/2, which you'll see I have right here. And then I plug 0 in to my 2x plus 1, which I get 1, which is exactly what I had here. So you get the same answer. It's just when you want to do the evaluation of your limit into the function. I prefer to do it first and change my limits so I have less to work with after I find my definite integral. Excuse me. All right. Some other interesting facts with integrals that might save you some time. Symmetry affects an integral. If we have an even function and we're taking the integral from the opposite of a to a of our function, what we can do is rewrite that, because with an even function, so I'll draw you a very basic even function. If this is the opposite of a and this is a, this area and this area are the same. So what I can do is just take 2 times the area on the right-hand side. And if you wanted, you could do 2 times the integral from negative a to 0. It just, it would give you the same answer. The reason I think the reason that I would go from 0 to a is many times this integral, when I plug 0 in, will give me 0 as an answer. So it just makes it a little bit easier to work with. This doesn't rely on substitution. Although when you do substitution, you might end up with an even function in terms of u, and then you could apply this. The more interesting one is if f is odd. If f is odd and you're taking the integral from the opposite of a to a, your answer is 0. So anytime you see opposite values for our limit, So anytime we have exact opposites, the first thing I would look at is the function even or odd? If it's odd, perfect, I don't have to do anything. I can just write 0 as my answer. If it's even, then if you want, you could rewrite the integral as 2 times the integral from 0 to whatever a is. Excuse me. If you didn't rewrite an even function, if you didn't rewrite the integral, what you end up with is whatever your value is at the upper limit minus the opposite of that value. So again, it works if you don't rewrite it. It's not a big deal. Just like if it was an odd function and you could take the integral, you would end up with a value minus that same value.